Good morning, lovely 12s. Right, buddies, I feel really lucky to get to teach you the next unit, my buddies, which is called Proof by Induction. So that's your title for today. Right, buddies, so this is at the tail end of the sequence and series unit, so I really hope that you've enjoyed that unit. It's quite a neat unit, sequence and series. And what happens is it actually finishes off with this is still in the sequence and series unit, but it's kind of like a topic in its own right. It's quite standalone proof by induction, because it's not just, it's not limited to sequence and series, not by any stretch of the imagination. It's a brand new way of proving stuff, though, which is really exciting. Now, you already know how to prove stuff in various ways, my buddies, believe it or not. Remember when you do trig identities and stuff like that? Remember when it's like you get those really hard trig stuff and there's some bits and bobs on the left and it's complicated on the left but it's simpler on the right, and you have to show that the left can equal the right? That's actually called a proof by deduction, and you do that by putting things in. You actually just get the answer. That's a proof by deduction. That's a type of proof that you know how to do. When you were at GCSE, there's a type of proof that you do, which is called a proof by exhaustion. Those are when you get like questions that are like, oh, what would it even be? It would be show something is true, and then you can show it's true for odd numbers, and then you can show it's true for even numbers. And since all numbers are either odd numbers or even numbers, it shows that it's true for everything. So that's a proof by exhaustion. There's another type of proof which you also know, which is called a proof by counterexample. That means you assume that something wrong is right, and then you essentially break maths with that, and then you're like, oh, actually, so the thing that I assumed was right is actually wrong, which means the thing that I was actually trying to prove is actually right. And that's kind of another type of proof. That's a proof by counterexample. But right at the very, maybe not top of the pile in terms of usefulness, but at the top of the pile, which I think, in top of the pile in terms of like logic and cleverness to it, is I think the proof by induction. So it's like described like climbing a ladder, but what I think I'm going to do before I explain is I'm just going to go through mathematically how you do it. It's 6 steps. It's easier than it looks, though, okay? So don't be too stressed out about it being complicated or whatever. We're going to go through 2 really nice ones together, and I'm going to give you guys a big chance to practice. Next lesson, what we'll do is we'll do a little bit more on proof by induction, but not with sequence and series anymore. We're going to focus on sequence and series today, but then next lesson we won't. We'll do other types of proof by induction, and then following that you'll get a great big revision lesson, so you'll be good at it even though it's complicated. So essentially, here's how proof by induction works. And I'll try to do the ladder analogy, and you should write it, okay? You do need to write this as a proper note because you're going to want it, okay? It'll help you structure your work. Okay, so here's how you do a proof by induction. First things first is you establish a base case, and that's where n equals 1. Now, you won't know what that means yet, but here's what it basically means in terms of a ladder, because, oh my gosh, for generations, every single person in the entire universe describes proof by induction using a ladder. I was taught with the ladder. Dr. Proud mentioned the ladder to me when we were talking about it initially. The textbook mentions the ladder. Online videos mention the ladders. Everyone's on about the ladder. So what the heck? Let's not be original at all. I'll explain it to you with regards to a ladder. Okay, step 1, establish a base case. That means, my buddies, if it were a ladder, you figure out that you can get onto the bottom rung of the ladder. Okay, so you figure out, you're like, yep, I'm on the ladder. Okay, next you assume that it works for all cases. Now, here's the thing. That means n equals k. You'll get that in a sec, though. Assume it works for all cases, which means this. Assume that whilst you have stepped on the first step of the ladder, just presume that if you were on anywhere on the ladder, that you'd be able to get to the next step of the ladder. Now, here's the next step. Get a target expression. So you'll have to see what that means in a sec. That doesn't work with my ladder analogy. Now, here's what you're going to do. Essentially, you are going to assume that you can get to a step on the ladder, right? So assume you're midway up the ladder or something. Now, if you can prove that you can get from where you are on the ladder, like some portion of the way up, to the next rung about that, the n plus 1 rung, or the k plus 1 rung, 1 rung more than you've shown that you can get from anywhere on the ladder to 1 step more than anywhere. Well then, my buddies, if you can get from anywhere on the ladder to 1 step more than anywhere on the ladder, and you knew for sure you could get to step 1, that means you can get from step 1 to step 2. And then by the same logic, that means you can get from step 2 to step 3, and 3 to 4, and 4 to 5, and 1,000,000 to 1,000,001, and all the way forever. Which means you've just shown that something works for every single number by using really, really, really clever logic. And so, if you can get on the very first step of the ladder, you presume you can take the second step, you can take every single following step. And that is exactly what proof by induction does, my lovelies. Cool beans. So, yeah, that's just kind of with a description in terms of words, but let's actually do it with some maths. How exciting. Okay, so here's what I'm going to get you guys to do now. Work out, yeah, so I've shamelessly nicked this from your textbook, a motivating example. Here's what I want you to do. To start with, buddies, just pop it into your calculator, pop it into your mind mentally, and have a look at this here. I've got a bit of a sequence going, or a bit of a series going. I have 1 over 1 times 2, then 1 over 1 times 2 plus 1 over 2 times 3, and then plus 1 over 3 times 4, and so on and so on and so on. To begin with, what I'm going to get you guys to do is to come up with what is called a conjecture for this. Now, a conjecture is what we think a pattern might be that's emerging. So, to start with, buddies, work out what all of those numbers are. Pause the video, go. Okay, and you're back. You should have found this. First one's a half, quite clearly. Then you would have to start using your calculator, using your mind properly then, and you would have got this then, buddies. So here's what I'm going to get you guys to do. We would like to come up with what is called a conjecture. Now, a conjecture, as I say, is it's kind of a pattern that we're trying to discern. It's a bit like a hypothesis would be in science. So a hypothesis to scientists is kind of what a conjecture is to mathematicians. It's something that we think is true, or we have a theory is true, but we're not for sure yet. We haven't proved it. So here's what you're going to do to start with. Have a little look. For sure it starts off like this. The first term in the series is going to be 1 over 1 times 2. Then it's going to be followed by plus 1 over 2 times 3. And then there's going to be plus a whole bunch of other ones, okay? Plus. Now, first term, second term, third term, fourth term. Okie doke, buddies. What I need here really is an nth term. So can you get me an nth term? Well, what's going on with the nth term? Well, check it out, my buddies. 1 over 1 times 2, 1 over 2 times 3. For sure the nth term is going to have a 1 on the top, because they all start with a 1 on the top on the left-hand side here, every extra term you're adding. But what I need to do is I actually need to link these numbers, the 1 times 2 and the 2 times 3. We need to link them to n for the term that we're on, if we're on the nth term. So what's the pattern here? What's going on? Well, in the first term, it was 1 times 2, the latest term in it. In the second term, it was 2 times 3. In the third term, it was 3 times 4. What's the link between the term that you are on and the numbers in the bottom? That's right, buddy. Whatever the first numbers are, my lovelies, whatever the first number is, it's n, okay? It's whatever term you're on. So the fourth one is 4 times 5. The fifth one will be 5 times 6, and so on. So what's the number it's times by? So the first number is the term you're on, and the next one's 1 more than it. Does that make sense? Now, what does it seem to equal? Well, it seems to equal, my lovelies. The fourth one had a 4 on the top, third one had a 3, the second one had a 2, so the nth one's going to have a n. And what's the link between top and bottom? Well, it's 1 more, n plus 1. This is probably the rule that governs the sum of this series. See what I mean? This is probably what happens. So if you had any number of terms, this is probably true. But it's not sufficient to say that this is probably true. We've got to be guaranteed it's true. Which means, buddies, dun dun dun, first ever proof by induction. Cool. So here it is. This is that exact sequence that you just said to me is probably true. And here's what we're going to do. We're going to prove it's true. Induction is the perfect proof for this because induction works brilliantly for sequences because induction deals with, okay, what would the next thing be? And that's exactly what a series and a sequence are. So these series that we're working on right now, that's exactly what that is, right? It's like add on the next one, add on the next one. So it's perfect for, perfect for induction. So let's do it. Here's what I'm going to do because I want to make it really clear and easy because I know it's complicated, but it's not going to be too bad. We're going to follow the steps perfectly. Step 1, make a base case. So here we go. I am going to write the number, but only just this one time. Okay, first things first is we need to have a base case, okay? Now, a base case is just to show that you were able to get onto the ladder. This is the first step, and you always just let n equal 1 because that's usually the easiest, okay? Now, here's what you do. On the left side of our equation, of our conjecture up here, here's what you're going to do. Well, the first term is just simply this one, right? Like that's the first term, second term, nth term, and this is the sum, right? So the first term on the left-hand side is simply 1 over 1 times 2, which means the left-hand side is just a half. What about the right side? Does it match up? If it's not a half, we're already scuppered. Well, n equals 1, so it's going to be 1 over 1 plus 1, which also equals a half. So brilliant. Base case established, buddies. That's that part done. Cool, cool, cool. Now, the most important step of all in these proofs by inductions is step 2. And this is where you do the assumption. So you're going to assume that it works for n equals k. Okay? You're going to assume that it works for n equals k. And if it does, buddies, here's what you're going to find. You are going to find then, if this does work for n equals k, and I'm going to switch colors because I'm going to come back to this one, this is very important. If it works for n equals k, it's going to just be this. It's just going to be 1 times 2 plus 1 over 2 times 3 plus the others plus the nth term. But the nth term is going to be the kth term now. K plus 1. You might be thinking, why do we bother switching the n out for k? It's because we're just trying to get one level separation from the thing that we're trying to prove here, and well, you'll see in a minute maybe. But yeah, if it's true, then this is true. Okay, we need one level difference. We don't want to use n's anymore because that's in the big conjecture. We don't want n's, we want something different. We assume that it works for n equals k. And if it does, then this is true. Happy days, buddies? Good. Because now we're ready for step 3, which is the target expression. Okay? Now, the target expression is what the answer should be if we went to the next one. So in other words, if n wasn't k, but k plus 1, this is proving that you're somewhere on the ladder, and now we're going to take one step more from where we are. One step more from where we are. Cool? Well, here's what that's going to look like, okay? On the left-hand side, it's just going to be this. It's going to stay the same. We're going to add one more term in, that's all. So I'm going to go back to blue, because this is less important. 1 over 1 times 2 plus 1 over 2 times 3 plus the others plus the nth term 1 over k plus 1. But don't forget, we're going one further. Plus, and we're going to do one further, right? So look up here, look at this part here, this nth term part up here. If we're going one further than that, my buddies, what we're going to do is we're going to swap n for k plus 1. So 1 over k plus 1, and this is going to be k plus 1 plus 1. I'll write it even. Cool. Now, that, my lovelies, should be equal to the right-hand side, but with k plus 1 in it, okay? So we're going to have k plus 1 in. So this should be equal to, and it will be k plus 1, we're doing green, I think that would match nicely, k plus 1 over k plus 1 plus 1. Now, I'll just leave the left-hand side alone just for the moment, and on the right-hand side then, buddies, that's going to equal this. That's going to equal k plus 1 over k plus 2. My buddies, that is the target expression, okay? That is the right-hand side of this thing here, is the target expression, okay? I'm just going to even label it. You don't label this in your normal proof, but just to teach you. Target expression, okay? In other words, if this is true, if this what I put in red is true, then that would by necessity mean that this has to be true. That's the target expression. Because now, my buddies, we're ready to actually go on to the proof. Okay? So, number 4. We are now going to prove, my buddies, that, and it sucks that I have to flick back and forth, that's okay. We're going to prove that the left-hand side of what would be in our target expression here, this left-hand side, we're going to have to actually prove becomes the right-hand side. Because remember how I did this? On the left-hand side, I just swapped in an extra term, the k plus 1 term, but on the right-hand side, I overtly stole this, didn't I? I just nicked that up there to make this. Well, we have to actually show that the left-hand side of the target one actually can become the right. So we're going to prove from the left-hand side for the k plus 1 case. Well, my buddies, if you want to prove for the left-hand side, check it out. It's going to be this. It's going to be 1 over 1 plus 2 1 over 1 times 2 plus 1 over 2 times 3 plus the others plus 1 over, what was it again? It was k plus 1, and then the extra one that we added in was this. It's plus 1 over, and I believe it was k plus 1 and k plus 1 plus 1. K plus 1 plus 1. Right, that's it. Okay, which means, my buddies, whew, a lot of writing down here, but that's okay. Here we go. Which means this, 1 over 1 times 2 plus 1 over 2 times 3 plus all the others, dot, 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 plus 1 over k plus 1, plus this, plus 1 over k plus 1, k plus 2. Okay, so there's where we are, okay? That's the left-hand side. Remember, my goal is to turn it into that. What's in yellow, okay? We want to hit that target expression. But we haven't yet. But if only there was something that we assumed was true. Oh, that's right. We assumed that it was true for n equals k. Can you see this part here, which I've done in red? Do you see this whole big section here? This, my buddies, oh my gosh, look at that. We said that all of this whole left-hand bit, so all the way to k plus 1, which is what's in blue here, is equal to k over k plus 1. So here's what you can write. You can just switch this out for k over k plus 1. Cool? Then you're left with the green. Plus 1 over k plus 1, k plus 2. Now, because that's the important step, you have to write down from assumption after, okay? From the assumption. Yeah, you assumed, my buddies, that all of this was equal to this earlier on in the proof, and now you just substituted it out. Cool. We're still not at our target expression, though. So what are we going to do? Well, we're going to go mental on algebra until we get the right answer. That's what we're going to do. Let's go back to blue, because that can be my basic color. Okay, let's add them together as fractions, because this thing was 1 fraction, and this thing is 2 fractions, so we need to get them together as 1. The denominator here is k plus 1, and this one's k plus 1 and k plus 2, so we'll times this one by k plus 2, and k plus 2, or cross multiply, however you prefer. And here you go. You're going to then get k plus 2, cool, over k plus 1, k plus 2, k plus 1, k plus 2, k plus 2, k plus 2, and then on this one here, it's just like plus 1 of the same, so I'm going to be lazy and just put it there in one step. Happy with that, my buddies? Because it would be like plus 1, because that already has the right denominator to it. Okay, cool. Let's keep going. Let's keep rocking on. Here we go. We're going to then get on the top. We're going to get k squared plus 2k plus 1 over k plus 1, k plus 2. Okay. It's still not what I want. It is 1 fraction, so it's certainly getting better because it's 1 fraction now, and it's relatively tidy, but it doesn't equal that. Yeah, it doesn't equal what's in yellow at the bottom. So what are we going to do? Well, I spot that the top factorizes. So 2 numbers that times to 1 and add to 2, it's 1 and 1. So it's k plus 1 squared, or k plus 1, k plus 1, to show you. And then this is over k plus 1 and k plus 2. Cool, which then we get to go whoosh, whoosh, and you're going to be left with just this. You're going to be left with k plus 1 over k plus 2. Well, oh my gosh, do you notice anything special about that? Anything special about that? It's the target expression. Oh my gosh, so we've done it. So here we go. You've just shown that it does work. Yeah, well, let's write it. Let's stop yipping and let's start writing. So here we go. Let's write it out. I'm going to make sure I nail this because there's a really efficient way of writing it. We're ready to go in, okay? So here's your conclusion, okay? 5. And we're going to make our statement. Okay. This is killing the proof. This is the final bit. Okay. So, if the result is true, the result is true for n equals k, because we assumed that it was, right? Then, it's also true for n equals k plus 1. Okay, so that essentially is your proof by induction, okay? So you've said if it's true for n equals k, you've just shown that it's also true for n equals k plus 1. Now, since it's true for 1, true, for n equals 1 then, well, what does that mean? It's true for n equals 2, because of course it is, right? Because if it was true for 1, it's true for 2. That's what we've just shown. It's true for n equals 2, and n equals 3, and and so on, and all positive integers. Cool? And that's it. So that essentially is your proof. Now the final thing then is to conclude it, okay? So here we go. Thus, by mathematical induction, and you just restate your hypothesis, your thing at the start. 1 over 1 times 2 plus 1 over 2 times 3 plus the others plus 1 over, what was it again? I can't even remember. 1 over n plus 1, wasn't it? N, and it's not k's anymore, n plus 1 is equal to n over n plus 1, n over n plus 1. Proved. Right then, buddies. So, for our last and final example, I've got this one for you, which is actually, it's actually a bit easier than the last one, to be honest. But if you wanted to, I don't know how comfortable you feel, but if you feel comfortable, why don't you go ahead and pause the video and see how far you can get, and see if you can actually get this solved, and see if we arrive at the same answer at the end. I would imagine that's not most of you, so most of you will probably still be with me. So shall we do it at a slightly faster pace? Yeah, let's do it. Okay. So, number 1, my buddies, what's the first thing that you have to do again? That's it. You're going to establish a base case. Okay? We have to show that it works for at least one number, and the number that we'll choose is the first number, 1, simply because it's the easiest. Which means on the left-hand side, it's just going to be the first term only in this series, and it's going to be 1 squared, which means the left-hand side equals 1. Now, same deal on the right side, but we've got that more complicated expression. Oh, I should show you as well. This is one of the standard. This is one of the what did you call them? Standard cases or whatever. These are one of the ones that you were just using. So I hope you recognized it. It's the sum of the squares, isn't it? So yeah, it's one of the standard results. How exciting! But anyway, on the right hand side, it's a 6th, and then n is 1. Then this is 1 plus 1, and this is 2 lots of 1 plus 1. And I'm hoping it just equals 1, so let's see. 1 plus 1 is 2, 2 plus 1 is 3, 3 times 2 is 6, divided by 6 is 1, so it works. So base case is established. Cool. What do you do for the second one, my buddies? The most important step of them all. That's right. You assume it's true for n equals k. Okay? Now, if you assume that it's true for n equals k, and the only reason I'm underlining and putting these numbers is to really help structure you. You can bin off the numbers and the underlines when you get quite good at it, but I don't know, it keeps me organized too. It's good, it's organized. Okay, if you assume it's true for n equals k, then that means this. That means that 1 squared plus 2, so just from the equation itself up here, 1 squared plus 2 squared plus the others, k squared, be the end one, is going to equal this. It's going to be a 6th of k plus 1, and then 2k plus 1. Okay? We just assume that that's true, okay? And that's going to be the most important step of this whole thing. Which means we're ready for step 3, which is to get the target expression. Cool? Now, the target expression, my buddies, is going to be this. It's going to be, well, here, I forgot to even write it down. It's for when it's n is equal to k plus 1. Alright, 4 n equals k plus 1 even. 4 n equals k plus 1. Now, what would happen for the next steps? This is how to get to the next rung of the ladder. Well, here's what it would be. The left-hand side would stay the same as it was. It's going to be 1 squared plus 2 squared plus the others plus k squared. But then we're going to go one more, aren't we? Because we're going to go to the k plus 1 one. So it'll be plus k plus 1 squared. Cool? It's just this n here popped a k plus 1 in for. Cool. And on the right-hand side, you're going to get this. It should be a 6th. And then k is actually going to be k plus 1, or n is k plus 1. then we're going to get k plus 1 plus 1. I'm going to write it just this one time. K plus 1 plus 1. You could just write k plus 2 if you wanted. This is going to be 2, k plus 1, plus 1. Cool. Just leave the left-hand side alone. It's not important yet. It will be in a moment. 6th, k plus 1, plus 1. And then this is going to be k plus 2. And then this, 2k. And that's going to be 2 plus 1 plus 3, that means. Okay, that's tidy. Would you agree? Good, because that is your target expression. What happens on the right-hand side when you pop it into the original equation is the target expression, okay? So that is your target, okay? We'd like to hit that. Cool. So we're ready to get to the meaty part of it now, my buddies. We're now going to prove it. We're going to prove that we can get the target expression. So we're going to prove from the left-hand side. Left-hand side. Okay. So here's what you got on the left-hand side. It was 1 plus 2 plus others plus k squared plus k plus 1 squared. Okay, so I'm just copying this because I flick back and forth. So we started off like this. We started off with 1 plus 1 squared plus 2 squared plus the others plus k squared plus k plus 1 squared. Cobains? K plus 1 squared. So that's what we've got so far on the left-hand side, right? Now here's the big thing. What do you do with this? Can you remember? What's going on with that, though? Well, what's going on with that? Well, do you remember? We assumed that that part I just wrote in red was equal to all of this noise, didn't we? A 6k, blah, 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 blah. We assumed that it was equal to that. Therefore, we can make the substitution. So it's a 6th k. All of this is from the assumption. It's a 6th k. I can't remember it. K plus 1. K plus 1. And was it 2k plus 1? K plus 1. Yeah, 2k plus 1. K plus 1 and 2k plus 1. K plus 1. And we'll leave this other part chilling. Plus k plus 1 squared. Now, it's important that you write for this one from the assumption. Okay, because that's not necessarily true yet. It's not true until we show that to get the target expression. So that's what we get. Okay, now here's where it gets nightmarish. You can see there's no plus in our target expression, right? It's 3 things times together. When you get multiplications together and no pluses, that screams to me, my lovelies, that screams factorize me. Now this is going to, because that's how you get rid of pluses, right? Like if I had 2 plus 4x, I'd factorize out a 2 to turn the plus into a times, because it'd be 2 and then times by some bracket, Cobains. So I want to factorize it. Now, again, looking to the target expression, it's got a 6th in the front of it. So even though a 6th isn't common here, I'm going to take a 6th anyway. So it's going to be tough factorizing. Let's do it. Who cares? Let's do it. We're hardcore. A 6th. Okay. What else is there? Well, there's no k's common. There is a k plus 1 common, so I'm going to take a k plus 1 as well. And the 2k plus 1 isn't common. So just because it is a hard factorizing, I'm going to switch colors to help. So we have the 6th and the k plus 1 already. That leaves k, 2k plus 1 from the first term. Now the second term, we pulled a 6th out of, which doesn't make sense. So we're going to have to put a 6 back in, and we're missing a k plus 1. Okay, I hope that you see that. A 6th times a 6 would cancel out. K plus 1 times k plus 1 makes k plus 1 squared. So we're right. Cool. Now we're just going to keep going mental on algebra, so let's do it. A 6th, k plus 1. Purple bracket is going to become circle bracket now because I'm going to try to skip steps. We're going to get 2k squared plus k plus 6k plus 6. Cool. Tidy. 6th, k plus 1. And in this one, it's going to be 2k squared plus 7k plus 6. So we're closer, but this has 3 brackets. Our target expression has 3, and we only have 2. If only there was something we could do with that second bracket, my buddies. If only. Oh, that's right, there is. It factorizes as well. So here we go, a 6th, k plus 1. And here we go, bracket here. Okay, let's do it. Let's do square. I'm going to do an extra step. Okay, square bracket. Here's what we're going to get. 2 numbers at times to make 12. So 2 times 6 is 12. 2 numbers at times to make 12, but add to make 7. So the numbers are going to be 4 and 3. So do I skip steps or do I not skip steps? I'm not going to skip steps. Apologies if you don't need this, but I'm going to not skip steps. Okay, 2k squared. You said the numbers were 3 and 4, didn't you? Plus 3k plus 4k plus 6. Factorize, factorize. 2k is common. No, it isn't. Just k is common, sorry. K, 2k plus 3. And on this one here, plus 2, 2k plus 3, plus 3, giving us an answer of k plus 2 and a 2k plus 3. Cool? Which, oh my gosh, buddies, is a sixth. K plus 1, k plus 2, 2k plus 3. Oh my gosh, does that look familiar? Oh my gosh, it's the target expression. Can you see we hit the target expression? Hooray, it is the target expression. Which means, my buddies, and see if you can remember the statement, because you have to be really careful how you write it. Which means, my buddies, that if the assumption is true, then it follows that the k plus 1 one is true, which means that it's all true, which means bish bash bosh, we proved it. So let's do the statement. Here we go. Are you ready? Here it is, the big exciting statement. Okay, so statement. And the statement's this. It says this. So, if the result, it's almost the same every time, is true, for k plus 1, for n equals k, then it is true for n equals k plus 1, for n equals k plus 1. Okay, that's what you just proved. Okay, you just show that it worked for n equals k plus 1 as well. If it worked for n equals k, it does work for n equals k plus 1. But since it worked for n equals 1, it works for n equals 1, then that means it works, then because k could be 1, right? Then it works also for n equals 2. N equals 2, and 3, and 4, and 5, and all positive integers. Which means it works for everything. And then the final thing, just to get the marks, 6. Thus, or so, or whatever you want to write, thus, 1 squared plus 2 squared plus the others plus n squared, back to n's, is going to equal a sixth. What was it again? A sixth, n plus 1 to n plus 1. A sixth, n plus 1 to n plus 1. And then why? By mathematical induction. Okay, induction. Now, it does get patterny, believe it or not, because I think it's tricky, I really do, but it does get patterny, and you'll have your head around it, and then you'll actually come to enjoy doing them. I enjoy them. Okay, so here we go. The work for today is page 89, questions 1 to 12, but just do a mix, okay? You can access them all, but I would suggest maybe starting not super hard. Like I started on question 8 when I was practicing it. I quite liked question 8. It was a good one. I'd recommend, but you can, yeah, pop around everywhere. Make sure you're trying a mix, okay? So some easy, some hard. Don't just do hard only. Don't just do easy only, okay? And there's a bit of a warning here. Steps and process are vital, okay? Like if you do this wrong at all, you could lose tons and tons of marks. So it's really thorough. The proof by induction is really reliant on those logic steps, so don't get them wrong. Make sure you're fully justified, even though it takes pages to do. So that's it for me. See you later. Bye, buddies!